In section 4 of our chapter on carbohydrates and nucleic acids, we're going to discuss the rings or cyclic forms of sugars. Sugars contain aldehyde or ketone carbonyls, and they also contain alcohol hydroxyl groups. So they can do an intramolecular reaction to make a hemiacetal. We've seen this reaction in our chapter on aldehydes and ketones as a part-way reaction on the way to forming a full acetal. We will discuss full acetals of sugars later in this chapter. Conceptually, it looks like this. An aldehyde sugar, for example, would have an aldehyde on the top of its carbon chain. It would then have a carbon chain, which we've represented by this curve. The carbon chain would have one or more chirality centers with OHs attached. And ultimately, there would be a chirality center with an OH attached, where the OH would be able to reach around and make a bond to the carbonyl carbon. This would probably occur under acid catalysis. It would be reversible, could be hydrolyzed back open. But effectively, because this OH in this portion of the chain reaches around to connect to that carbon, and the rest of the chain is still attached, we go from creating an open chain into creating a ring. The ring itself, if we look at the aldehyde carbon, no longer has an aldehyde. It now has a hydroxyl group and then an oxygen connected to carbon, an OR group, attached to it. And we call this a hemiacetal, which is basically halfway to a full acetal. The cyclic forms of sugars are called furanoses or pyranoses, depending on if they have a 5-membered ring or a 6-membered ring. This comes from the corresponding 5 or 6-membered ethers that we covered in our chapter on ethers. The 5 and 6-membered ring ethers have common names. The common name of the 5-membered ether with 2 pi bonds in the ring is furan, and the corresponding 6-membered ether with 2 pi bonds is called pyran. So if we look at, for example, the cyclic form, a common cyclic form of ribose, we can see that it would have a 5-membered ether-like ring similar to furan. So it is named as a furanose. Similarly, if we look at a common 6-membered ring structure derived from glucose, we can see that it would have a 6-membered ether similar to pyran, and therefore it is called a pyranose. The names of the cyclic forms of the sugar are actually different from the names of the open chain forms. The name of the cyclic form is made by replacing the SE in the open chain name with either furanose or pyranose. In biochemistry, the cyclic forms of sugars are sometimes drawn using Fischer projections. That would look like this, where we imagine using D-glucose, right, left, right, right, taking the hydroxyl group on carbon 5, the hydroxyl oxygen would then make one more atom in the ring, and then connecting that back up to the carbon at carbon 1 at the top of the chain. So it would create conceptually a structure that looks like this, although that right angle does not represent another carbon. It just represents the fact that we have to kind of turn the corner with the ring. We can then count out the number of atoms in the ring, starting from our hemiacetal carbon as 1, 2, 3, 4, 5, oxygen 6, back to 1. Hence the 6-membered ring. Biochemists often use this type of representation, but it's more common for organic chemists to use what's called a Haworth projection. In a Haworth projection, we imagine that the ring is lying on its side and that we're looking from a side view, and that the groups attached to each carbon of the ring are drawn perfectly parallel to the edge of the paper, either straight up or straight down. Very often in Haworth projections, we will not draw the hydrogens because the structures can become quite crowded. This then would be the Haworth projection of this Fischer projection of a pyranose form, a cyclic form of glucose. It should be noted, very interestingly, that in almost all of the cyclic sugars, it's not the hydroxyl group on the very end of the chain that makes the bond. Instead, it is more common for hydroxyl groups that are higher up on the Fischer projection to make the bond. Very often, it's the hydroxyl group that is one from the very end of the chain, as in this case. This creates a small carbon chain sticking off of the ring. I'm going to call this the tail because I need some way to designate this small carbon group when we talk about stereochemistry in these ring forms. I'm now going to cover how we can convert from a Fischer projection to a Haworth projection. What we're first going to do is identify which carbon and which OH is going to form the ring. We then want to count how many atoms would be in that ring. So for example here, using this carbon, this OH on glucose, we would have 1, 2, 3, 4, 5, 6 atoms in the ring, including the oxygen. What we're then going to do is draw a side view perspective drawing of a ring of that size. So here is a 6-membered ring, side view perspective. We are also going to put the ring oxygen in the back, and we're going to put carbon 1 on the right. It's often helpful to number the Haworth projection so that we can transfer the groups on the corresponding carbons of the Fischer projection to the correct carbon of the Haworth projection. What we're then going to do is write all of the groups except the tail, which should be on carbon 5, and the hydroxyl group, which is formed on carbon 1 when we make the ring. All of the rest of the groups can be written with a simple rule. We look at the Fischer projection. If the group is on the right, we draw it down on the Haworth projection. If the group is on the left, we draw it up on the Haworth projection. If you recall, in glucose, the groups were right, left, right, right. In this case then, what we see is that carbon 1 was the aldehyde, carbon 2 would be on the right, so it would be down. Carbon 3 was on the left, so it would be up. Carbon 4 was on the right, so it would be down. We haven't drawn carbon 5 group or the OH on carbon 1 yet. We're next going to put the tail onto the ring. The tail will be either up or down depending on which direction the OH that formed the ring was on the original Fischer projection. if the OH was on the right, for example, as it would be in D-glucose, then we draw the tail on an up bond, as shown. In contrast, if the tail were on the left, we would draw it on a down bond. Finally then, carbon 1 is the newly formed hemiacetal, which has O carbon, so oxygen to carbon 5, and then an OH attached. We're concerned about which direction the OH would be oriented. It turns out that a 50-50 mixture, in theory, could be created. 50% of the time or so, the OH could be up, 50% of the time it could be down. We have a way of naming these two diastereomers of the pyranose or furanose molecule. If the OH is cis to the tail, we say it is the beta diastereomer, stereoisomer. If the OH is trans to the tail, we call it the alpha stereoisomer. If the stereochemistry is not specified, very often we draw a sort of a wavy bond to indicate that either it's a mixture or we don't know which or we don't care which. Examples of these are shown below here. Here are some examples of the various stereoisomers of the Haworth projection of glucopyranose that we've been working on. So for example, here we see that the hemiacetal hydroxyl group is in an up position cis to the tail. We would call this the beta stereoisomer. Here is the alpha stereoisomer, where now the hemiacetal hydroxyl group is in a down position trans to the tail. And then finally, here's an example of a ring where we are not specifying the stereochemistry of the hemiacetal. It turns out that the pyranose forms of the sugars are six-membered rings. And in first semester organic chemistry, we discussed the importance of the chair form of six-membered rings, the chair drawing of the conformation. This actually represents probably pretty close to the most accurate three-dimensional drawing of these six-membered ring sugars, these pyranoses. To convert from the Haworth projection to a chair conformation, we're going to use the same methodology that we used in first semester, designating bonds as either upper or lower on each carbon, and then looking at the chair and designating the corresponding bonds as upper or lower, and then transferring the proper corresponding group. So for example, if we look at the carbon 1 hydroxyl group, it is on an upper bond. If we come over to this chair and we look at the two possible bonds on that carbon 1 carbon, we can see that one would be here, equatorial, the other one would be axial, pointing in the direction of the point parallel to the paper. Therefore, the axial group would be lower and the equatorial group would be the upper. So we will transfer the OH on the upper to the OH on the upper equatorial bond on carbon 1. You can see that then we can continue this around the ring to get this structure for beta-D glucopyranose. This is a really interesting structure to organic chemists because if we look, all of the large groups are equatorial. This leads us to believe that the beta form of glucopyranose should be the more stable form of that ring